Welcome to another Avaya Technology session. In this updated series of presentations, we will be providing you with the content that was presented at the 2015 Avaya Technology Forums. The Avaya Technology Forum is the place where the latest technology developments and trends are discussed with Avaya's most experienced and brightest engineers and architects. While the value of the interaction with our experts cannot be replicated here, we are coming as close as we can by bringing you the presentation content. In this session, we will discuss the ease and technical superiority of the support of IP Multicast on Avaya's SDN-FX Fabric Connect. I'm Ed Kohler, and I will be your host for this session. Sometimes it's good to begin with a humorous point. The comment in the slide was made by a customer who has since converted their IP Multicast deployment over to Fabric Connect. For those who are currently running a network that supports PIM, or Protocol-Independent Multicast, the humor may have a bit of a sting. For those who have never been involved with IP Multicast, it can serve as a heads-up warning. PIM environments can be very difficult to deploy, difficult to maintain, and very difficult to scale. We've had IP Multicast for quite some time now, but why the sudden need for a change? First, IP Multicast has taken on a much more central role in the way applications work, not only in the delivery of media to multiple viewers, but also for critical data center functions as well. This has put a spotlight on the fact that the traditional approach of protocol overlays is grossly inefficient, and this tends to limit the scale and resiliency of the service. This is all due to the fact that at the lowest level, the Ethernet forwarding or data link MAC layer, the forwarding works on a stateless flood and learn model. While no one can argue the utility of this tried and true method for end system mobility, no one will also argue the fact that the requirement for flooding in the core is something of a necessary evil, and if possible should be avoided. As a result, we dice up the network topology with layer 3 networks and introduce routers to create a sense of end-to-end network paths. Additionally, for IP multicast services, we typically overlay yet another protocol such as Protocol-Independent Multicast or PIM, which enables for the registration of multicast sources and solicitation or joining to a service by a received subscription. All of this leads to an environment with strong dependencies between the protocols, and where any network topology change will create a disruption of the service. Sometimes this disruption is on the order of 20 to 30 seconds, but usually they will extend into several minutes in duration. A quick look at a series of diagrams illustrates the reasons for this. As we can see, the process of known MAC forwarding is very straightforward. The bridge or switch will reference its forwarding table and act accordingly. The method for unknown MAC forwarding is also fairly straightforward. As we can see, the bridge or switch simply floods the frame out all ports and waits for a response. If the MAC is on the network, it will send a responding frame. The bridge or switch then updates its table and then will use the known MAC method for forwarding data to that MAC address as long as it remains valid. This seems like a simple model, and it is. The problem is that this was way back in the early 90s. Things have changed drastically in the industry since the inception of this model. This is brought home by a fairly simple core network. As in the case of all network cores today, there are multiple virtual LANs, for which all intents and purposes are to be viewed as flooding domains. We also have a router that interconnects the VLANs by the use of some type of internal gateway protocol such as OSPF or RIP, but in a single router instance, even this is not required. As we can see, things are quite a bit more convoluted, even in this simple model, once these new logical elements are added to the topology. Flooding is no longer so straightforward. As a very simple example, let's say that Station A wants to send a frame to Station C. The first thing that Station A will do is send out an ARP request for Station C's IP address. The Ethernet address will be all Fs. This indicates a broadcast or flood. The router in the middle switch will in turn perform a proxy ARP on behalf of Station A. Due to the fact that the VLAN that Station C is located on traverses the core, the flooding must traverse to all switches servicing that VLAN. This needs to happen even though station A and C are on the same switch. Here, flooding is not so straightforward, and it is further frustrated by IP's need to use broadcast or flooding to resolve IP addresses to MAC addresses. Note that this has to occur whether MAC-C is known to the edge switch or not. Now let's add in multicast. As you can see, things get even more complex. Protocol-independent multicast requires a complex set of protocol functionality to provide for the registration of the source via rendezvous point registration and the solicitation of interest via IGMP at the edge. Note how PIM runs on top of and is directly dependent on the unicast routing protocol that it rides on. In the case of this example, it's OSPF. At the lowest level, we have the traditional stateless flood and learn forwarding environment. If any changes occur to either of these lower layers, the delivery of the multicast service is disrupted. This lends to an environment that is complex and touchy. Network topology changes and expansions are overly complex and intrusive to the service. Also note that this is for one routing environment only. In multi-tenant networks, this has to be replicated for every tenant that requires separate IP multicast services. This creates an environment where the number of software state machines becomes prohibitive and begins to affect the performance of the overall network service. Now, there has been a lot of hype around the word fabric in the industry, but they all deal around the issue of a forwarding path. The way that different fabrics solve this problem, however, are vastly different, and some lead to architectural cul-de-sacs that limit the functionality and scale of the given technology. Spanning tree, which is part of the 802.1d standard, is the traditional protocol for Ethernet topologies. It basically works on an active-passive topology that allows for redundancy but not load sharing, which requires an active-to-active topology. Avaya has pioneered switch clustering, or SMLT, to provide for this active-to-active topology, but it does so in a model that is still stateless in the way that it behaves. On the other end of the spectrum, we see multi-protocol label switching, or MPLS. This is a very feature-rich model that not only resolves the issue of paths, but does so for multi-site as well as for layer 3. But it is a very heavy overlay model that requires a complex cocktail mix of protocols to function. The end result is an environment that is very complex to provision, maintain, and troubleshoot. In between, there was a huge chasm of capability that existed for quite some time. Recent fabric approaches have attempted to close this gap. Trill and its cousins, Fabric Path and VCS, from Cisco and Brocade, respectively, attempt to solve this problem for Layer 2 virtualization. However, these approaches are still root bridge dependent due to the fact that spanning tree is an integral function within the fabric, but it also still works on the concept of large flooding domains. As a result, VLANs remain the primary element for virtualization within the fabric. This results in a very limited fabric technology that only supports L2 at the single site level. Juniper's QFabric, which borrows from the OpenFlow concept of separating the control from the data forwarding paths, creates a scenario where the topology is extremely limited due to the logical size of the fault domain. This solution has recently fallen out of favor in lieu of the new metafabric architecture, which is in reality a respin of existing products. Additionally, it also uses VLANs and flooding as major elements within the fabric. Cisco has recently moved to a new architectural alternative in their acquisition of Enciame. But again, this is focused on leveraging respins of existing products and technology. And HP is still very much on the fence with no clear direction that can be seen. IEEE 802.1AQ, or shortest path bridging, provides for a new method of abstraction for superior virtualization at new levels of scale. This new innovation allows for service-based virtualization and the ability to do it at geographic scales that no other fabric can accommodate, with the exception of the complex suite of protocols that comprise MPLS. Avaya has also done significant research and development around SBB to enhance the protocol to support L3 virtualization, as well as true IPVPN methods for end-to-end multi-tenant environments. Additionally, we have added native IP multicast capabilities to allow for the end-to-end delivery of true IP multicast within a multi-tenant network without the need for MPLS or VRF Lite. As you can see, Avaya's Fabric Connect provides for a next generation of virtual services infrastructure that needs to be compared to MPLS rather than to the other Fabric technologies. They are simply in a different class. So what is it about shortest path bridging that makes it so superior? Well, the technology can be broken down into three major components. First, the fabric works on a stateful topology, and this topology is supported by ISIS, which is a very extensible protocol that works on the use of type length value fields, or TLVs. RFC 6329 provides for the required TLVs to support IEEE 802.1 AQ, and IETF Draft Unbehagen provides for the TLVs to support L3 virtualization or IP shortcuts, as well as L3 IPVPNs. Recent research and development as well has resulted in the creation of new TLVs to support the end-to-end fabric for IP multicast. Its feature set is available on every Avaya switching platform that is capable of running advanced services. These new TLVs have been submitted also to the IETF in the interest of open standards, foundations, and frameworks. Second, the fabric uses a universal forwarding label provided for by an earlier IEEE standard known as 802.1 AH. This encapsulation method provides areas for information that, when used in conjunction with ISIS, provides for the vast array of virtualized services within the Avaya Virtual Services Fabric. Third, the fabric uses a new level of abstraction for virtualized services. These provision service paths are termed as ISIDs, or individual service identifiers. These elements are a new method of services abstraction within the 802.1 AQ standard, and as we shall see, they provide an important role in the delivery of native IP multicast on shortest path bridging. First of all, nothing gets forwarded into a shortest path bridging network without the sense of a path. As a result, there is no stateless forwarding within it. This results in a very deterministic method for the movement of data. This all starts with the establishment of a network topology. As we can see, once the switches establish adjacencies with one another, they exchange a series of type length values which provide for the network topology. Once a complete network sequence is created, the Dijkstra algorithm is run. Here we show the resulting shortest path Dijkstra tree for SBB node 0.00.01. The number is the nickname of the SBB node. It is basically a short-form identifier, the use of which will become obvious in the next series of slides. But for now, it's an alphanumeric string which uniquely identifies an SBB node within a domain. Also, each SBB node is identified by an actual Ethernet MAC address known as the BMAC, or backbone MAC address, which is provided by 802.1 AH. Each SBB node also runs Dijkstra from its perspective, resulting in shortest path trees to each SBB node within the network. Here we show each tree in a color-coded fashion for clarity. 802.1 AH works in conjunction as follows. As the 802.3 frame is ingested into the SBB network, it is encapsulated into an 802.1 AH frame. The destination and source BMAC addresses of the SBB nodes are used as the universal delivery labels. The original 802.3 frame is carried along, totally intact, as payload. This is termed as the CMAC, or client frame. As the frame is ingested at SBB node 0.00.05, it uses the shortest path knowledge of that SBB node. The bold green arrow shows the shortest path across the network. Once the BMAC frame is delivered, it is de-encapsulated and the end station receives the frame. The SBB network is in essence transparent to the end systems on the stateless flood and learn Ethernet edge. All forwarding in the SPB network occurs by the use of BMAC addresses and the shortest paths. The end result is a very stateful, deterministic forwarding model that does not use flooding. This is because all forwarding always occurs over a path. But there is a problem. How do we support and facilitate a flooding functionality across the SPB network without flooding within it? This requires us to take a little closer look at the 802.1 BMAC frame. This slide shows 802.1 in comparison to earlier virtualization standards, which are based on the element construction of virtual LANs, which we recall are broadcast or floating domains. As can be shown, the concept of the VLAN is still carried on in the CMAC subframe within the 802.1 BMAC frame, but the 802.1 frame adds in a 24-bit field to represent this new form of abstraction called the ISID. This 24-bit field yields a services capacity that is numerically at 16,777,215. This new abstraction increases the virtualization capacity of the fabric exponentially. It is important at this point to clarify what an ISID is. It is not a broadcast or flooding domain. It is a subset of Dijkstra shortest path trees. It is also based on BMAX within the ISIS link state database. For now, we will leave it at that, but it is important to point to remember as we move forward. So the 802.1 frame gives us quite a bit of information to use in order to move data across the network. Let's take a closer look at how these ISIDs can be used to create virtualized services within the SPB network. If we relate an ISID to something, we create what we at Avaya term a Virtual Services Network, or VSN for short. If we attach an ISID to VLANs, we create a Layer 2 VSN. These are useful in any instance where you would use queue tagging within a traditional network core. In essence, a VLAN can be extended virtually anywhere across the SPB network regardless of distance. Uses for this are guest VLANs, voice VLANs, L2 connectivity between data centers for services replication, or VM mobility. L2 VSNs are also very useful for the distribution of SCADA protocol environments, such as those used for programmable logic controllers and remote terminal units in transit authorities, power grids, automated manufacturing, and many other use cases. ISIS is also a powerful protocol for routing IP. As such, IP shortcuts allow for the forwarding of IP data with L3 forwarding by the shortest path across the SPB network. While IP shortcuts do not use ISIDs, they always use the shortest delivery path generated by ISIS. If we attach an ISID to VRFs, we create a Layer 3 VSN. This combination yields an L3 IPVPN environment that is useful for multi-tenant requirements where services separation is a must. Additionally, a tenant can be anything from an actual company, a department, or a group, to an application or a set of services delivered within the cloud. Finally, VSNs can be routed to provide internetworking capability. The end result is a vast range of topology options that can be created using combinations of the various service offerings. In order to provide for an insight as to how multicast works within an SPB network, we will take a focus on the L2 VSN. As we clarify certain functions, we will then view them in context of the other service offerings. Recall that we still need to provide a flooding functionality across the SPB network without actually flooding within it. So how does 802.1 AQ accomplish this? The standard uses a model known as constrained multicast or tandem replication. This could have all been accomplished fairly easy by the establishment of a special flooding BMAC address, which uses all Fs. The SPB node would then flood all ports associated with a given ISID. But it was realized that multicast is algorithmically one of the most difficult problems in networking. Multicast addressing is always a destination addressing paradigm, and as such, a multicast address, whether layer 2 or layer 3, is never topologically significant. In other words, we always have to resolve the address to the source. The next step after that is, of course, to resolve the path, or RPF, back to the source. As we can see, the RPF is largely solved for already by the knowledge within the fabric. SPB works on the basis of shortest path distribution trees, so the sense of an RPF can be resolved simply by resolving the source. SPB also eliminates this requirement by the use of the nickname discussed earlier. What constrained multicast does is it creates a multicast destination BMAC based on the values of the nickname and the resident ISID in which the flooding event is required. As we see in the diagram, IP end station 10.10.10.10 sends out a broadcast ARP for 10.10.10.11. SPB node 0.00.01 ingests the frame and encapsulates it into an 802.1 AH BMAC frame. It uses its own BMAC as the source, but for the destination BMAC, it creates a custom multicast address and encodes the value of its nickname as well as the resident ISID that the frame needs to be replicated against. Note how both the source and RPF are already known to the SPB network. The very base functionality of 802.1AQ resolves two of the most critical challenges to multicast. There is no need to resolve the source or the RPF as they are already known at the outset. This enables SPB to emulate a flooding functionality without actually flooding within the network. The basic theory of operation for SPBM multicast is fairly straightforward. First, the implementation reserves the use of higher-order ISIDs with those of a value greater than 16 million. These ISIDs are now reserved as dynamic circuits that will serve as the IP multicast distribution trees. A multicast source is registered into the environment by the creation of a dynamic ISID at the backbone edge bridge where the source resides. The backbone edge bridge then propagates its advertisement by the use of specific ISIS type length values. There are two defined: TLV 185 for constrained multicast services, to be used in instances where you wish to constrain or scope a particular multicast domain to a particular virtual service network, and then also type length value 186, which is global and is intended to work at the global route table or VRF0 level. The actual ISID itself is not extended out until there is a solicitation of interest by a multicast receiver using simple IGMP v2 or v3. Once the solicitation is made, the ISID is automatically extended out to the receiver, and multicast data will begin to flow. This slide illustrates a very simple reference diagram. As multicast data is sent into the network user interface at the edge of the Fabric Connect network, a dynamic ISID is automatically created and advertised. The receiver then simply solicits interest. Let's take a look at all of this in action. Recall that there are 16,777,215 ISIDs. Native SPB takes the upper value ISIDs from 16 million on up and uses them dynamically to create IP multicast distribution trees. Remember that each ISID is a subset of the Dijkstra link state database of each node. As such, ISIDs are the perfect delivery vehicle for multicast services. In this example, end station 10.10.10.10 is now a video server, sending video into group 239.1.1.1.1. As it sends multicast data into the SPB network, SPB node 0.00.01 establishes a high-order ISID for the multicast group. It then provides for an update to all SPB nodes in the network by the use of special TLVs within ISIS. Now every node in the SPB network knows that to join multicast group 239.1.1.1.1, one would attach to ISID 16,000,001. At this point, however, there are no interested subscribers, so the ISID is not extended out into the network. as IP station 10.10.10.12 issues an IGMP join for multicast group 239.1.1.1, SPB node 0.00.05 attaches to ISID 16,000,001. The same thing occurs for station 10.10.10.11 as well. The only functionality required at the edge is IGMP snooping. Now, for a true multicast engineer, something important becomes apparent, and it is actually something phenomenal. In the legacy approach, multicast is controlled within the L2 VLAN by the use of IGMP snooping, which is simply a flooding filter. Here, the network acts in a stateful distribution tree, even within the L2 VLAN. Note how ISID 1000 is now shown in dotted lines. This is because constrained multicast is not used to distribute the IP multicast service within the VLAN. A separate stateful distribution tree via ISID 16,000,001 is provided, and this happens for each and every multicast group. Note that there is also another subnet and a station of the IP address 10.10.11.10 that is also issues an IGMP join for multicast group 239.1.1.1. Even though the station is on a different subnet, the same ISID is used to extend multicast services across the L3 boundary with the Layer 2 services distribution tree. The result is the ability to traverse L3 routed boundaries without the use of traditional multicast routed interfaces. Note here that we are using TLV 186 for unconstrained multicast services. The end result is a very stateful and deterministic delivery model for IP multicast services that delivers both scale and performance. Also, due to the fact that the multicast distribution tree is an ISID, the failure convergence times for IP multicast delivered over an SPB network is extremely fast, in the order of 100 milliseconds or less. This convergence time is more than fast enough to be totally transparent to any application or service that is being delivered. Now let's take this one step further. Here we see an L3 VSN that links several subnets together by the use of VRFs in ISID 5100. This is a totally separate virtual network that is not even visible to the outside world. None of the subnets or VRFs are visible or accessible. Note how the core functionality does not change. The only major delta is that there are now VRFs at the edge. They will serve as the active IGMP queriers for the multicast services. Beyond that, only IGMP snooping is required at the L2 Ethernet edge. Notice how in this instance, ISID 16,000,002 is created and advertised out to all other nodes in the SPB network. Now any other station within the L3 VSN can join to the given multicast group, but no one outside the L3 VSN can join. No one outside the L3 VSN can even see it. Note that we are using TLV 185 for constrained multicast services as we wish to scope this service to L3 VSN 5100. This is useful for types of multicast that require true services separation, such as multi-tenant television delivery, or services that require complete security and total isolation, such as IP video surveillance. What are its use cases? Literally any service that would have used traditional multicast in the past can strongly benefit from native multicast over SPB. Applications like TV and video distribution are a couple of obvious examples, but there are many critical technologies that depend on IP multicast functionality as well, such as high-definition digital video surveillance, particularly for large distributed environments. Due to its very nature, isolation and security are of paramount importance. Avaya's Fabric Connect resolves this requirement easily by the use of native multicast within the L3 VSN environment. This approach allows for performance and scale, but also provides for complete and total separation from the rest of the network environment. As a result, a customer could use native SPB multicast to deliver video and UC services out to the wider core, and also use it to provide for secure video surveillance between data centers and out to the network edge without being concerned about the accidental or intentional crossing of network services such as those that might be attempted in a DOS or spoofing attack. There is simply no other technology available today that can provide these services in such an optimal fashion. Thank you very much for your attention. As you can see, Native IP Multicast over Avaya's Virtual Services Fabric truly sets a new bar for virtualized multicast services. With it, IP Multicast is finally ready for the cloud. To summarize today's session, we covered Fabric Connect's next-generation implementation of IP Multicast on SPB. Recall that the Fabric utilizes ISIDs to establish multicast distribution trees rather than the complexities of IP reverse path hop-by-hop routing. Also, due to the fact that ISIDs are not based on IP as a routing protocol to establish these paths, they are in essence invisible to typical IP and multicast scanning techniques, which adds for both stability and security. Some of the largest IP multicast deployments in the world are now based on Avaya's Fabric Connect technology. They have made PIM an acronym of the past. So, what are you waiting for? Thanks for your time today. I hope that you found the video both helpful and informative. Stay tuned for the next video in the ATF series soon to be posted, End-to-End Security with Fabric Connect and Secure Encryption.